Hi, we're Team 5, and I'm Saravya.
I'm Sayukta.
I'm Sam.
I'm Josh, and this is the Escape Room.
We designed an Escape the Room game consisting of a team of 2 autonomous rovers versus 1 human-controlled rover. The human-controlled rover, Captor Rover, sits at the opposite end from the Rescue Rover. The first part of the game, the Rescue Rover navigates to the Trapped Rover and presses a button on the front of the Trapped Rover, activating the rover. Once this happens, the goal of the game is for the Trapped Rover to follow the Rescue Rover to safety before the Captor Rover is able to navigate and intervene, blocking them from escape. In this example, the autonomous rovers won. In the next example, you will see a game where the human-controlled rover wins.
Here is our server application GUI. Our server needs to handle a few things. It needs to be able to concurrently handle messages coming to and from the server. And as you can see here in this widget, it can handle messages from any of the devices concurrently, and it will print that out onto this table with timestamps. It also needs to handle game states. Most of it's handled in the back end, and you don't have that much control on the screen, although you can start, stop, and reset once the rovers are connected. Here's a widget to manually control each of the rovers. The Captor needs manual input to be able to move because it has no autonomy. The other rovers do have autonomy, but if they do get stuck, you have the option to manually move it if necessary. Here is another debugging tool. This just allows you to send a one-off message if any of these widgets do not have the ability to send the message you want to send. Here is a visual to see the IR sensors if there's any rovers putting data on the screen. And here are some widgets that, again, debug. It allows you to see the internal states in the state machines for the rovers. And here we can toggle different messages. This is the package format that we're using to communicate information between the rover and the Raspberry Pi. It's divided into 6 fields. A is our sequence number, B is the message size, C is who the message is for, D is who the message is from, E is the message type or importance of the message. At the end, we have the message itself. If we look at our example, we have 20 is our sequence number. That means it's the 20th message that the rescue has sent to the Raspberry Pi. 4 is the number of bytes within our message. Rescue is who the message is to. Pi is who the message is from. Motor is the importance of the message. So this is a message to the motor thread on the rescue rover, and this is the message itself. A and B are used for error handling. C and D are pretty self-explanatory. E is used to filter out messages based on who the messages are made for within a device. We only had one limitation with our server. That's the Wi-Fi server connection. Wi-Fi's are pre-configured and will automatically connect to the server once being powered on. Our biggest issue with that is timeouts when idled. When there's no messages being sent, they like to turn off or disconnect from the server. We fix that with two parts. One is from the rover that will occasionally send out a heartbeat message that's otherwise useless but just sends some type of communication to the server. And the other one is a reconnection state in the back end of the server. Once the Wi-Fi is disconnected, it will try to reconnect by sending another useless message. Otherwise, we had no range issues, we had no message dropping issues, it worked flawlessly.
I will be talking about the message handling on the rover side. The rover side message handling consisted of 3 threads: the UART send thread, the receive thread, and the central control thread. Let's talk about the UART send thread first. The UART send thread was mainly responsible for sending the messages to the server. It enforced that the message format on the message being sent was absolutely flawless. It also made sure that any error on this side was caught on the server by sending bad messages when debugging was enabled. Bad messages range anything from a missing header, missing footer, to an incorrect message size of the actual message. Now that we have seen how the messages are sent to the server, let's see how the messages are being received on the rover side. The receiving is mainly handled by the UART receive thread. As soon as a message is received, it goes through an error checking routine. It makes sure that the message is not missing a header or a footer, and it's received to its complete size. After the actual message is extracted, it's sent to the control thread for future actions. Now let's move on to the central control thread. The central control thread is basically responsible for controlling all the rover game states. Depending on which rover it is, the game states differ. So the central control thread ensures that the rovers are in their required state. For example, the rescue rover starts in the active state as soon as the game start signal is sent to it, while the captor and the trapped rover start in the idle state. This is because the rescue rover has to start moving as soon as it gets a signal, while the trapped waits for the rescue to find it. Because the captor rover is human controlled, the central control thread also allows for manual control to the rovers.
For our sensors, we chose an IR sensor array consisting of 8 sensors. And the way that the sensors work is that they shoot an infrared light onto the surface that they're looking at. They then charge a capacitor. So in order to measure the color that they're seeing, what we did is we have a timer interrupt that's triggered every 5 milliseconds that measures the time it takes for the capacitor to discharge. It then packages that information into an unsigned int and sends that to the sensor thread. Within the sensor thread itself, it interprets the sensor data it gets and determines where the rover is on the line. So for our situation, in order to be considered as following the line, the sensors 3, 4, 5, and 6 have to be seeing white. And white is considered as a smaller number, so if it takes less time for the capacitor to discharge, then it's considered as seeing lighter colors, so like white. And if it takes more time, then it's considered seeing darker colors like black. So the sensor thread gives commands to the motor thread and asks for help to the server. In the situations that the sensor thread sends help to the server, is only if it's at an intersection, so where it sees all white, so all 8 sensors are seeing white, or if all 8 sensors are seeing black. If it's all white, then it's considered as an intersection. If it's all black, it's an error state, and it's asking for help to get back on the line. The times that the sensor thread sends commands to the motor thread is when it's seeing a forward, left adjust, or right adjust. So if one of these sensors starts seeing white, 7 or 2, it's considered as either left or right adjust, and it sends the appropriate command to the motor thread. We faced a couple of different limitations when it came to the sensors. The very first one was the battery power. If the battery was completely charged, the sensors could more distinctively tell the difference between white and black, whereas if the battery power was low, it couldn't tell as clearly what's black and what's white. A couple of the other limitations that we faced was the lighting in the room in conjunction with the height of the sensors on the mounting plates on the rovers, so where they were placed on the rovers basically. Both of these affected how much reflectance the white tape was shining on the sensor array. With that said, there were a couple of improvements that we could have done. The main improvement was the integration of the PID algorithm. It would have made the sensor reading a lot less sensitive to these limitations. It would have made it more easier for us to integrate and test with.
The motor control thread takes advantage of the PIC32 in conjunction with the motor shields to execute commands for the rover platform, allowing our embedded system to navigate our arena. The command thread can accept up to 10 different commands. This state diagram demonstrates the autonomous rover, which executes the forward, pause, right turn 90 degrees, left turn 90 degrees, adjust right, adjust left, and halt commands. The motor control thread operates on all 3 of our rovers. When they're powered on, it'll go through its initialization and then block in this state until the specific rover becomes active in our game. So when the rescue rover receives the game start signal, it'll immediately start receiving commands from the sensor. The first command that the sensor will feed it is the forward command, which will take it down here to the switch statement and kick it into the forward state. It'll remain in the forward state until another command other than forward is received from the sensor thread. An example of this would be that the rescue rover is drifting off the line and needs to make a right adjustment. For the captor rover, it also becomes activated when the button on the trapped rover is pressed. The main difference is that rather than the sensor thread feeding the commands to the motor, the commands are coming from buttons on the server. So once it becomes active, it will not have a command available and will go into the pause state until the user presses a button indicating which direction it wants the rover to drive in. In the case that it's forward, it would exit the pause state, go to the execute next command. The switch statement would put it into the forward, causing the motors to start driving forward, where it would remain in that state until the user presses a left turn or right turn, or pause, or reverse. The right turn, left turn, adjust right, and adjust left commands all operate on a timer sequence. While they're in the right turn, left turn, any of the turn states, they do not accept any commands from the sensor thread, but instead send a signal to the sensor thread telling the sensor that the motors are busy and are not able to accept a command right now. Once these commands are finished executing, it then sends a motor free signal to the sensor to tell it to remain executing the commands. In the case that it does arrive at a waypoint, the sensor will send it the pause command, which will halt the motors and put it in the pause command and remain in the pause command until the server tells it which direction it needs to go at the intersection. One issue we found when executing the motor commands in this fashion were that the commands would be based on the battery pack level. So if the battery was very low, the right turn wouldn't turn right quite as much and the left turn wouldn't turn quite as much, whereas when it's all the way fully charged, it would overturn a little bit, or underturn, or overturn on the other way a little bit. One possible solution for this would be to implement the encoders on the motor, where you could count the number of ticks rather than just simply use a timer and just count the amount of time that the motors are on.